Welcome back to the channel. So today we're going to talk about electrical units that you're going to encounter when working on cars, or anything really. So let's center outside. I want to show a couple things here that are kind of fascinating to me anyway. Alright, this is my beater truck. Big block Ford F-250. 460 cubic inch. And what we're going to do is we're going to measure the battery cable diameter on this truck. It's a 12 volt system. And let me take the micrometer real quick. And let's measure these cables. Alright, negative cable 0.322. So, third of an inch. Positive cable 0.333. Once again, third of an inch. And let's walk over here to my 1939 Ford 9N tractor, 6 volt system. And we're going to measure the battery cables on this ancient beast and see what diameter they are. Alright, positive cable first. .433 inches. And now the negative side. .42 inches. If you're wondering why the negative cable goes to the solenoid, this tractor is positive ground. Now, the interesting thing is this is a 120 cubic inch engine. It's only 6-to-1 compression. It does not take a lot to spin it over. So why is the 6 volt cable significantly larger than the 12 volt cables on an engine that's 3 times bigger? So to understand why 6 volt cables are so much bigger than 12 volt cables, we need to understand how power works in electrical circuits. But wait a minute, I'm getting ahead of myself. There's a few other terms we need to learn first. So right off the bat, we need to learn resistance, which is ohms, which is simply the resistance to electron flow. So electrons in the outer shell of a copper atom, in this case, flow from one atom to the next, and ohms, or resistance, is the resistance to the electron flow. And then we have volts. Volts is the pressure behind the movement of the electrons through copper atoms. So ohms and volts. So what's power? So power is watts. And the way that we figure power is we take the current of the circuit, which in this case is going to be amps, and we multiply that times the volts. So amps times volts equals power in watts. So what does that have to do with cable size? So in order to understand the difference between 6 volt and 12 volt systems, we need an analogy. And a good one to use is water. So let's say that we have a water pipe that's that size, and we have a water pipe that's this size. Two vastly different sized pipes. Now, clearly this one's going to flow more water. But is there something we can do to the smaller pipe to make it flow the same amount as the bigger one? Well, the answer is yes. We can increase the pressure. So if we increase the pressure enough on the smaller diameter pipe, we'll increase the flow rate through that pipe, and at some point we can equal the amount of volume of water that's coming out of the larger pipe. So the analogy in this case is pressure is voltage. So if we have more voltage in a system, we're able to force more electrons through that circuit, and we can actually equal the current flow in a circuit that has much less voltage. In this case, our analogy for this is our 6 volt system. Our analogy for this is our 12 volt system. Now for some terminology. So we've already established that pressure is volts. And we need to understand the other terms that we use when we're dealing with electronics. So the next one we're going to talk about is resistance. Which we measure in ohms. And we need to talk about current. And that's expressed in formulas as I, but when we're dealing with it, it's a large A for amps. And then the last thing we need to talk about is power. And it's almost always in watts with what we're dealing with. And then we need to know the relationship between all of these units. And to do that, we need to know Ohm's law. Ohm's law is pretty simple. To find resistance, we take the voltage and we divide it by current. To find the current, we take the voltage and we divide it by the resistance. If we don't have the voltage but we have current and resistance, we can multiply resistance by current and we can get voltage. Simple mathematical relationship. And then power is even simpler yet. Power is just simply voltage times current. If we take voltage times current, we have watts. So this is important when you're dealing with low voltage, high current systems. And in both 6 and 12 volt systems, that's exactly what we're dealing with. So let's do a little thought experiment here. Let's say that we have a 12 volt system and we have a starter that's drawing 100 amps. In actuality, when you hit the key on that particular system, it's not going to be 12 volts. The battery voltage will pull down. It will probably pull down to something around 10 volts. So starters consume such a large amount of current that they will pull the voltage source down a little bit. So 10 volts while you're on the key, 100 amps. And can we figure out the resistance of that starter by having those two numbers? Well, yeah, we can. If we take the voltage and we divide it by the current, we'll end up getting the resistance of that starter while it's spinning. And we do that, it ends up being 0.1, almost wrote amps, 0.1 ohms. 0.1 ohms. The resistance of a starter in circuit is 0.1 ohms. That is an extremely low resistance value for a component. And it has to be that way because in order to get enough power out of a starter motor to spin an engine around, we need extreme amounts of current because we're limited in our voltage. In this case, 10 volts. And we can figure our wattage too. If we take 10 volts times 100 amps, that equals 1,000 watts. So some starters may be more than this, some starters may be less than this. A diesel starter might be 4 times this amount, in which case this would be 4 times less resistance. But suffice to say, starters pull an extreme amount of current. So we've already determined that our theoretical starter needs 1,000 watts to spin an engine over at a certain RPM so that it will start and run. So now let's deal with a 6 volt system. And in this case, when we hit the key in a 6 volt system, it will once again pull down a little bit, probably something around 5 volts. So in order to equal this 1,000 watts, how much current do we need? So if we're dealing with 5 volts, everything remained the same except our voltage divided by 2. This is pretty easy math. Our starter is going to have to pull 200 amps on a 6 volt system in order to spin the engine around at the same speed, same RPM as our 12 volt system starter at 100 amps. So once again, this will equal 1,000 watts. But we need twice as much current to get there. So interestingly enough, whenever you double voltage,
you reduce your current requirement by half. So when going from 6 volts to 12 volts, our cable went from
0.42 inches,
0.33 something. Significant decrease in diameter. And that relationship holds true even at much higher voltage levels. For instance, this is a typical 14 gauge house wire. That 14 gauge house wire would move enough watts to start an engine at 120 volts line current. So we can get the same amount of current out of this, or same amount of power, I should say, out of this 14 gauge wire at 120 volts as our 6 volt system can get out of a cable that's
over
4/10 of an inch in diameter. Okay, now let's talk about voltage drops. So voltage drops in a 6 and a 12 volt system are critical. If you could imagine our theoretical 12 volt starter, which actually in circuit is 10 volts, and it's pulling 100 amps, and its resistance is 0.1 ohms, and that gives us 1,000 watts. And we need that 1,000 watts to spin this engine at somewhere around 150 to 350 RPM so that it starts. 0.1 ohms. Let's say that you had a battery with corroded connectors, corroded terminals, and the connection between the terminal and the battery cable has severe corrosion, and where the eyelet bolts to the starter is corroded, and the total sum resistance of all that corrosion is 0.1 ohms. What you've essentially done is you've cut the power going to your starter in half, because at each one of these junctions we're going to drop the same amount of voltage. So without this, here we have our battery. Here we have our key. Here we have our starter. And when we hit the key, our source voltage becomes 10 volts, and all of that voltage is dropped across the starter. So if we were to take a DVOM and we were to measure the voltage drop across that starter, we would measure 10 volts. Now we have a corroded positive cable that equals 1/10 of an ohm. And let's say it's between the battery cable and the key, or the solenoid. In this case it would be the solenoid that's driven by the key. So this is 0.1 ohms right here. If we were to take that same DVOM and we were to measure between the positive post and the solenoid, we would also measure 10, well, no, I'm sorry, we would measure 5 volts. Because half the total battery voltage would drop across our resistance and the other half would drop across the starter. So there would be a 5 volt drop from here to here and a 5 volt drop across the starter. We cut our source voltage in half, we cut the power going to the starter down to 500 watts. Just with 1/10 of an ohm resistance between the positive post of the battery and the starter. So voltage drops are critical. This is one of the reasons you can't really use DVOM on ohms to measure battery cable resistance, because most meters, especially auto-ranging meters, aren't very accurate at such a low resistance value. They're not really reliable measuring such low resistance values. So you can use this method to check the voltage or check the resistance of the circuits going to a high current device. In this case, and I've done this many times, in order to check the resistance of a positive battery cable, you can set your DVOM on volts, and you can just measure the drop between the positive post and the starter stud when you hit the key. And typically, you shouldn't see it drop very much. If you see much more than 1.5 volts when you hit the key, that indicates a problem, a pretty serious problem. So 1.5 volts taken away from your source voltage of 10 volts, that's significant. So voltage drops are a good method to find problems with high current systems in cars. Something else you can use voltage drop testing for is fuses. Let's say that you have a parasitic draw in a vehicle. It used to be we would just take the battery cable off and put a test light between the battery cable and the positive battery post, and if it lit the test light, we'd know there's an excessive draw. That doesn't work very well with modern vehicles, because if you pull power away from a module, it may consume much more current at low voltage levels, like the voltage supplied by a test light, for instance, than it would be if it was fully powered up. So you can't just disconnect modules in a modern car to check parasitic draw. So one thing you can do is just get to the fuse box and you start taking voltage readings across the top of the fuses. All fuses have resistance. So if you look at a typical blade fuse, it looks something like this. And this thin part right here is calibrated to provide a certain amount of resistance. And the amount of resistance that it provides is gauged or sized to create just enough heat at a certain current flow to melt this copper. So a 10 amp fuse, when there's 10 amps flowing through this little narrow band of copper, it'll create just enough heat so that this will melt and open up. So all fuses have resistance. They have to have resistance in order to work. So when you run power through any fuse, there's a voltage drop across the fuse. And you can measure that. And you take that voltage reading that you're getting across that fuse, and you can actually plug that into charts online that are available and figure out what the current is that's flowing through that fuse. Because if you have a known resistance, and you know your source voltage, you can do the math, use Ohm's law, and find out what the current is flowing through that fuse. So, in this case, if you're looking for a parasitic draw in a vehicle, you can just start checking fuses in the fuse box. If there's no current flowing through a fuse, there should be no voltage drop across it. You'll read 0 volts. If there's current going through a fuse, then you'll start to read voltage, and the higher voltage will indicate higher current flow through the fuse. And you can accurately determine parasitic draws as low as 100 milliamps using this method.
So here we are back to our original question. Why is a 6 volt cable so much larger in diameter than a 12 volt battery cable? And the answer is because we've handicapped the system with 6 volts. We don't have a lot of pressure that's pushing electrons through the system, and because of that, any resistance in any component makes a difference in a 6 volt system. So a smaller diameter cable going from the battery to the starter would induce just enough resistance to pull enough current away from the starter to drop our power level down below acceptable values. This is why 6 volt cables are so big, because the pressure going through the system, the pressure to push the electrons from one copper atom to the next is so low that we need a conductor that's huge in order to move enough current to get our power that we need to spin the starter over. I hope you liked this video. If you did, please subscribe. And hey, thanks for watching.